Let's consider another one of Einstein's thought experiments to uncover a new consequence of the fact that the speed of light is constant between observers in different reference frames. This new experiment is set up very similar to the one we used to derive time dilation, where Isaac stands on a planet and Albert flies by in a spaceship at velocity v. In Albert's ship, he uses the same apparatus consisting of a laser pointed at a mirror and a timer which starts when the laser fires and stops when the pulse returns to the laser. However, this time Albert will rotate the apparatus so that it lies parallel to his direction of motion. In Albert's frame, the distance from the laser to the mirror will be given by delta xa over 2, and so the total distance the light will travel according to Albert is just delta xa. When Albert conducts the experiment, the time that his stopwatch measures, given by delta Ta, will just be delta Ta is equal to delta Xa divided by c. Rearranging for the distance, we find delta Xa is equal to c times delta Ta. However, from the time dilation equation, we already know that the time measured in Albert's frame can be given in terms of the total time measured in Isaac's frame, delta Ti, by delta Ta is equal to the square root of 1 minus v squared over c squared times delta Ti, or delta Ti divided by gamma. Plugging this into the equation we have for the distance that Albert sees the light travel, we have delta Xa is equal to c times delta Ti divided by gamma. Now, Isaac's timer will be a bit modified from the previous experiment. Since the experiment is moving in the direction in which the light is traveling, Isaac will see two different path lengths. The first will be the path between the laser and mirror, which will be extended due to the fact that the mirror recedes away from the light pulse. The second will be the path back from the mirror to the laser, which will be shortened since the laser travels toward the light pulse. So Isaac rigs his stopwatch so that it will give one time, call it delta T1, once the light pulse hits the mirror, and another time, delta T2, when the light pulse returns to the laser. The total time that Isaac measures will simply be delta T1 plus delta T2. The distance that Isaac sees the light travel over the first leg will be given by the length of the apparatus according to Isaac, given by delta xi divided by 2, plus the extra distance that the mirror travels when the light pulse is in transit, given by v times delta t1. Similarly, the distance Isaac sees the light travel over the second leg will be given by delta xi over 2 minus the distance the laser moves towards the light pulse, given by v delta t2. Since the time the light spends traveling will just be the distance traveled divided by the speed of light, we can write the times that Isaac measures as delta t1 equals delta xi divided by 2 plus v delta t1 divided by c, and delta t2 equals delta xi over 2 minus v delta t2 over c. Since delta t1 and delta t2 appear on both sides of their respective equations, we have to solve for each, which gives delta t1 is equal to 1/2 delta xi divided by c minus v, and delta t2 equals 1/2 delta xi divided by c plus v. The total time that Isaac measures will just be the sum of these two times and will be given by delta Ti equals delta Xi divided by c times 1 minus v squared over c squared, or gamma squared delta Xi divided by c. Finally, we can plug this into the relationship we found between the distance that Albert measures and the time Isaac measures to find delta Xa is equal to gamma delta Xi, or flipping the location of gamma, delta Xi equals delta Xa divided by gamma. But what is this equation saying? If we remember that gamma is always greater than or equal to 1, it becomes clear that this is saying that lengths measured in Albert's frame along the direction of motion appear squished to Isaac. However, what if we give the apparatus to Isaac instead of Albert? From Albert's perspective, Isaac is traveling at the same velocity v that Isaac sees Albert travel, just in the opposite direction. Therefore, all the same arguments apply, and we find that any measurement made in either of the frames will look squished in the other frame. So, Albert's spaceship will look shorter to Isaac than Albert, but Isaac's planet, though spherical to Isaac, will look like an oval to Albert. This idea is known as length contraction. Time dilation and length contraction are the two main ideas at the very core of special relativity. With these, we have successfully reconciled the fact that the speed of light does not change between reference frames. More importantly, we have discovered that if someone tells you you're looking old and chubby, all you have to do is jump in a spaceship and speed by them.